Welcome to the Deep Dive. I'm your host, and today we are jumping right into a topic that honestly feels like a massive invisible line was just crossed in artificial intelligence.
Yeah, it's great to be here. We've got a lot of fascinating source material to cover today.
We really do. And our mission for this deep dive is to translate these huge AI improvements, specifically looking at Google's Gemini 3.7 Flash, into plain English for you, especially if you're entirely new to the field.
Right, because for the last couple of years, playing around with AI has felt a bit like, hiring a brilliant but incredibly distractible intern.
Yes. Like, you could ask it to write a beautiful poem or summarize a massive legal document, and it would just spit something out in seconds.
Exactly. But the moment you asked it to manage a complex multi-step project, it would completely lose the plot. It would invent a totally new set of instructions halfway through and leave you to clean up a spectacular mess.
But today, it seems like that intern just put on a suit. We're officially moving from AI as a fun party trick into an era where it's a reliable digital coworker.
To really understand the magnitude of that shift, we need to look at a concept emerging right now in software engineering. It's called the workhorse model.
Okay, a workhorse model. What exactly does that mean?
Well, the sources we're diving into make it very clear that Gemini 3.7 Flash wasn't built just to win an academic test or, write the most eloquent essay. It's optimized for execution, reliability, and scale.
So it's about getting actual work done.
Right. It specifically targets complex knowledge work, real-world software maintenance, and autonomous systems. It's essentially designed to be the engine of an enterprise.
I want to break down how it actually operates, because the underlying math of how an AI completes a job is surprisingly unforgiving.
It really is. The math of mistakes is where this gets fascinating.
Let's use a simple analogy for a multi-step agent workflow. Think of setting up a line of dominoes. Say you give an AI a 5-step task, right?
It's like a basic office workflow.
Yeah. It needs to read a database, extract a user's complaint, summarize the issue, draft a refund email, and hit send. 5 steps. If each domino has a 95% chance of falling correctly and triggering the next one, my initial thought is that sounds pretty good. A 95 is a solid A in school.
It sounds great until you do the compounding math. In an autonomous system, a 95% success rate is actually an absolute disaster.
Wait, really? A 95% is a disaster?
Yeah. The math from our sources lays this out perfectly. You don't average out to 95% overall. You have to multiply those probabilities together.
Oh, right. Because step 2 depends on step 1.
Exactly. 0.95 to the 5th power means your total workflow only succeeds about 77.4% of the time.
Wow. So nearly 1 out of every 4 times you ask the AI to handle that refund process, the chain just breaks somewhere.
And in a business setting, a process that fails 23% of the time isn't just an annoyance. It means the system is basically useless.
Yeah, you would spend more time monitoring and fixing the workflow than if you had simply done the task manually yourself.
Right. But observe what happens when you boost the reliability of each individual step just slightly, up to 99%. 0.99 to the 5th power jumps your overall workflow success rate to over 95%.
That is wild. So a tiny 4% bump in step-by-step accuracy translates to a massive jump in real-world reliability.
It does. Higher success rates matter immensely for long workflows. That's why multi-step planning errors compound so badly over long task durations.
That makes total sense on a mathematical level, but I'm trying to visualize what is actually happening inside the AI's brain. Like, why is it so hard to just carry a thought through 5 simple steps?
Think of it like playing the game of telephone with yourself over 5 days. When an AI acts as an agent, it makes a decision, calls an external tool, reads the result, and decides what to do next based on that specific result.
Okay.
If it slightly misinterprets a tool's output on step 2, say, it reads a date format. Wrong step 3 is going to be based entirely on a hallucination.
Oh, I see. So by step 5, it's totally lost.
Exactly. By step 5, the AI isn't just failing. It is confidently executing a flawless plan based on a reality that no longer exists.
It essentially corrupts its own context window.
Precisely. And that is why Gemini 3.7 Flash's focus on robust error management and instruction following represents a fundamental strategic shift.
Because it knows when it's confused.
Yes. The AI is specifically trained to recognize when it doesn't understand something, to stop, and to either ask a human for clarification or double-check its previous work. It's no longer about raw intelligence, it's about task persistence.
That's a great way to put it. Knowing the answer to a trivia question is one thing, but actually being able to cook a 5-course meal without burning the kitchen down is a totally different skill set.
Yeah, absolutely.
Now, I want to look at what happens when it applies that persistence to writing software, because I have to play devil's advocate for a second here.
Go for it.
ChatGPT and other tools have been generating code for you and me for a while now. If I need a quick script to calculate the total cost in a shopping cart, I just ask for it. So isn't this new model just a slightly better version of autocomplete? Isn't writing a single function easy compared to untangling a massive, messy corporate code base?
Your skepticism is completely justified. And it highlights the exact distinction our sources draw between traditional coding assistance and modern iterative agent execution.
Okay, so there's a real difference.
A huge difference. Generating a basic function in isolation, like your shopping cart script, is straightforward. The AI doesn't need to know anything about the rest of your website, it just writes the math.
Right. It's just a standalone math problem.
But real software engineering lets nothing like that. Your code never exists in a vacuum. To actually engineer software, the agent has to navigate sprawling, messy corporate repositories.
Yeah, because if I change the shopping cart math, it might accidentally break the tax calculator or like the shipping module on a totally different page.
Exactly. Real-world software maintenance tasks require understanding intricate dependencies between hundreds of different files. If the agent is asked to fix a bug, it has to act like a detective. It runs search commands to find where a variable was first created, reads the developer notes attached to it, modifies multiple components at once, and then crucially, it runs trial tests in a sandbox environment.
Oh, wow. So it actually tests the code before finalizing it.
Yes. It checks to see if its fix actually worked or if it accidentally broke that tax calculator you mentioned.
So it's not just guessing the next line of text. It's actively verifying its own work.
Yeah.
That is way beyond basic autocomplete.
And the data deep dive from our sources really proves this shift. There's a benchmark called Frontier Code, which measures that standard basic code generation we were just talking about.
Okay, how did it do there?
Gemini 3.7 Flash saw a respectable 27% relative gain. Good, but not earth-shattering.
Right.
But then there's DeepSWE version 1.1. This benchmark is specifically designed to simulate complex software engineering tasks, repository navigation, and real problem solving.
The hard stuff.
Exactly. And on that metric, the performance jumped by a massive 33% relative to the previous model.
A 33% jump on complex engineering tasks. That completely changes the categorization from a code generator to a true implementation agent.
It really does.
And the sources mentioned a fascinating application of this in web development. They talked about transforming visual Figma screens directly into production-ready React components.
Yeah, bridging the gap between design and engineering.
For those not deep in web dev, usually a designer creates a visual mock-up in Figma. They draw the boxes, pick the hex codes for the colors, set the typography.
Right.
And historically, a human developer has to look at that picture and manually translate the visual spacing into actual code.
Which is a process that is notoriously tedious and, frankly, very prone to human error.
But this implementation agent can consume those Figma screens directly. It looks at the visual layout, reads the underlying design systems, and just spits out functional React components.
The functional interactive building blocks of modern websites.
Yeah. It even writes the routing, meaning it programs how clicking a button on page A seamlessly transitions you to page B.
An agent transforming a visual bounding box directly into a functional user interface completely changes the boundary of who does what in a product organization.
But wait, I have a question about the budget here.
Sure.
If the AI is constantly running trial tests in a sandbox, acting like a detective, and looping through its own code, isn't that going to absolutely nuke a company's server budget?
That's a very common concern.
Because cloud compute isn't free? Every time the AI thinks, the company pays for the computing power. If one model costs, say, $1 per million tokens and another costs $2, isn't it a no-brainer for a company's budget to just buy the cheaper one?
You're touching on a massive debate in the tech world right now regarding the economics of AI. To understand it, we actually have to throw away the standard metric companies have been using, which is cost per token.
Oh, really? Why?
Because it's basic math applied to the wrong variable. The sources introduce a far more important metric for these agentic workflows: cost per successful task.
Cost per successful task. Okay, walk me through that.
Let's look at the cheap $1 model. It's inexpensive to run a single query, right? But because its reasoning isn't as sharp, it hallucinates a bug.
Okay, so it messes up.
Yeah. It requires 5 retries. It makes 4 unnecessary external tool calls trying to find the right file. And finally, a human engineer has to spend 45 minutes untangling the mess and correcting the final output.
Oh, wow. So you aren't just paying for the initial prompts. You're paying for the retries, the extra database searches, and the hourly rate of the human who had to step in.
Exactly. Now contrast that with the $2 model. It costs twice as much upfront to plug into its API, but it solves the task in 1 or 2 iterations with 0 human intervention.
Because its initial reasoning is sound.
Right. It takes the most direct path to the solution. So the $2 model is vastly cheaper to run in production.
That is the true hidden cost of a bug. The initial price tag is a total illusion if the system requires constant babysitting.
Our sources define this dynamic as first-pass quality multiplied by recovery capability.
First-pass quality. Getting it right the first time.
Getting it right and being capable of recovering gracefully when it inevitably hits a weird edge case. If it can do both, it practically eliminates the time spent on manual code corrections.
And these reliable workhorse models drastically speed up software development cycles, bringing massive economic benefits to company budgets.
Knowing that this highly accurate first-pass reasoning is now economically viable changes everything about how software companies build AI systems.
Right, because if the actual brain power is cheaper and more reliable, it seems like companies will no longer just buy one giant, super expensive AI to do everything.
Exactly. You don't have to rely on a single brain. You can start building teams of AI. Our sources call this the shift toward model portfolio economics.
Like that phrasing, model portfolio economics. Sounds like delegating tasks like a manager assigning work to different departments.
That's exactly what it is. Let's compare the historical blueprint with where we are heading. Historically, companies relied on what we'll call Architecture A.
Okay, what is Architecture A?
You use one incredibly powerful, incredibly expensive model call to do the whole job in a single pass. It's streamlined, but it is highly prone to single-point failure.
So if that one monolithic model gets confused midway through the task, the entire output is ruined. The single domino falls off the table.
Yep. Now enter Architecture B, which relies on model routing. Instead of one giant risky call, you utilize several cheaper, specialized calls in an iterative loop.
Like having different departments.
Exactly. You design a system where one AI agent acts as the planner, breaking down the project ticket. It hands a plan off to a researcher agent, which finds the relevant legacy code.
Okay.
The researcher gives context to the executor agent, which actually writes the new script. The executor hands it to a validator, which acts like a rigorous QA tester. And if the validator finds a bug, it kicks it to a repair agent, which fixes it and sends it back.
That is literally a software firm in a box. You have project managers, coders, and testers autonomously checking each other's work.
And because Gemini 3.7 Flash makes that high-quality reasoning so much cheaper, a company can afford to have the AI double and triple check its own logic without bankrupting the server budget.
And I imagine the business value of reaching this scale is profound.
It's massive. It makes autonomous reasoning affordable enough to automate sprawling, multi-step business workflows that were previously just too expensive to touch.
Like what? What's an example of something too expensive to touch?
Think about a massive, tedious job like a full repository migration. Say a company needs to update thousands of legacy code files to a new security standard.
Oh, a job that human developers actively avoid doing. It's soul-crushing work.
Exactly. If you assign that to a team of senior engineers, it takes them 3 months. That is incredibly expensive in terms of human capital, so the company might just delay the security update for years.
Right, because hiring more human developers just for that is too pricey.
But if an agentic system using Architecture B can map the dependencies, update the code, run the validators, and complete the entire migration over the weekend for a fraction of the cost, that trapped productivity is suddenly unlocked.
So the goal isn't necessarily to replace the human developers. It's to execute tasks that the company simply couldn't afford to assign to a human in the first place.
Precisely. You're doing work that would have otherwise been ignored.
Which just brings up a really important question for anyone listening who works in tech or knowledge work. If the AI agent is now planning, executing, validating, and fixing its own code in an autonomous loop over the weekend, what exactly is the human developer doing all day?
That is the million-dollar question. Agentic AI changes where human effort is concentrated. The human role shifts entirely away from manual execution and towards system architecture.
It sounds like developers are moving from being the people manually digging the ditch one shovel of dirt at a time to becoming the architects designing the entire aqueduct system.
That analogy perfectly captures the evolution of future developer career paths. The daily responsibilities shift dramatically upward.
Because you aren't moving the dirt anymore. You're deciding where the water needs to flow.
Right. Previously, the human workflow was linear. You receive a ticket, write the implementation, write the test, submit for review, and deploy.
Very step by step.
The new model is supervisory. Engineering teams are evolving away from prompt engineering, simply asking the AI for a snippet of code, toward what the industry is calling agent engineering.
Agent engineering. Okay, walk me through what a developer is actually doing on a Tuesday morning if they were an agent engineer.
Instead of typing out raw syntax, the developer is designing the workflow itself. They define the agent's roles within Architecture B.
Setting up the planner and the validator and all that.
Yes. They set the constraints and tool schemas, meaning they determine exactly which internal databases the AI is allowed to access and which ones are strictly off-limits.
Oh, they're setting the guardrails, making sure the autonomous system doesn't accidentally drop the production database while trying to fix a typo.
Exactly. Strategic risk management becomes a massive part of the job. The human builds the evaluation criteria, defines the objectives, and reviews the weird, complex exceptions that fall outside the AI's standard processing capabilities.
So the human moves from raw content and code production entirely over to workflow design and quality control, going from a tactician to a strategist.
And what's really wild is that this elevation of the human role isn't limited to just software engineering.
Really? Where else is it happening?
The sources explicitly highlight that Gemini 3.7 Flash also saw a massive jump in document reasoning. There's a metric called the GDP document benchmark, and it went from 22% to 34%.
That's a huge leap.
It is. And if you think about it, most enterprise workflows outside of the engineering department are fundamentally just document workflows.
True, like what, HR or legal?
Yeah. Consider a major internal policy change. If HR updates the remote work policy, a human normally has to rewrite the handbook, draft the announcement email, update the legal compliance forms, and track down managers for sign-offs.
A lot of busy work.
But an AI with high document reasoning doesn't just write the text faster, it executes the workflow surrounding the text. It cross-references the old policy, updates all downstream documents simultaneously, and schedules the necessary approval meetings.
It stops being a fancy writing assistant and becomes a full-on operations coordinator.
Exactly.
Well, we have covered a tremendous amount of ground today, peeling back the layers on how AI is fundamentally changing the nature of digital work.
We really did.
We started with the compounding math of mistakes, exploring why a 99% success rate is the absolute baseline for autonomous agents. We saw how that reliability transforms basic autocomplete into real software engineering, capable of navigating messy corporate code.
And we explored the budget-saving economics of getting it right the first time.
Right, moving past the illusion of the cheapest token price. And finally, we looked at how this elevates the human worker from a coder to a strategic architect through agent engineering. It really circles back to the idea of the intern putting on a suit.
A highly reliable coworker.
Exactly. But as we wrap up this deep dive, I want to leave you, the listener, with a final thought to mull over. Something that builds on everything we've unpacked today.
What is it?
If the financial and temporal cost of actually executing complex software drops to near zero because of these workhorse agents, does the true value of a software engineer shift entirely away from knowing how to code to simply having the imagination to know what needs to be built next?
That is a fascinating point. When the friction of execution disappears, human imagination truly becomes the ultimate bottleneck.
Think about that the next time you're staring at a blank screen. The tools to build the aqueduct are practically running themselves. What are you going to build with the water? Thanks for joining us. We'll catch you on the next deep dive.